In this ether chapter last semester, we did not learn about the ring-open ring reactions of epoxides, nor did we learn about the Clayton rearrangement. So that's what we're going to do in this semester. The epoxides are named by naming the alkane underneath and then numbering where the oxygen is attached and using the term epoxy. So if you look at this basic structure underneath is ethane here. And where's the oxygen attached to the 1 and 2 carbon, so we call it 1,2-epoxy ethane. This is the simplest nomenclature. There's other ways to name, but this is the one I expect you to know for the exam. Now, let's practice with this. If we look, we can see our basic alkane is a cyclohexane. And where is the epoxy? Well, because it's a functional group, we want to put it, have the lowest numbers for it. So I'm going to call this 1, 2 or 1, 2. Which would work best? Well, if I go in this direction, that gives this group a 4. If I go in this direction and give this group a 5. So I'm going to go this direction. That gives us 1, 2 epoxy cyclohexane, and then the cyclohexyl attachment, the substituent of cyclohexyl, is on the number 4 carbon, and so it's 4-cyclohexyl. We know how to form epoxides. Last semester we learned that we could take alkenes and treat them with MCTPA, or any peroxy acid would do the same thing. Another way is to take the alkene and treat it with a first chlorinate it, and then with water in the presence to make a halohydrin, and then treat it with a base, and that base does basically essentially an SN2 attack, and the chloride leaves, and we make an epoxide. But this is old stuff. What we're going to do now is learn how to open the ring. So here is a ring opening reaction. If I treat this epoxide with a little bit of acid, it protonates that oxygen. This can now open and put a positive charge here. But even if it were to open and put a positive charge here, the non-bonding pair on the oxygen is still going to be very, very close to that positive charge. So the nucleophile, which is water here, is going to do an underside attack so that we get a trans diol. So we have acid hydrolysis to give trans diols. Our other reactions are going to be very similar to this. If I treat it with a hydrohalic acid, so this would be hydrochloric acid, hydroiodic acid, hydrofluoric acid, the acid is going to protonate this oxygen. And then what's going to happen is the nucleophile is going to do attack from the opposite side, from underneath. So we get a trans halohydrin. It's basically the reverse of a halohydrin being treated with sodium hydroxide. But there are some conditions on this. That was a symmetrical epoxide. What happens when it's asymmetrical? Well, let's go back to cleaving ethers. We remember last semester we learned that hydrochloric acid will cleave ethers. It protonates this, and then what happens is, because that is not tertiary there, it is primary and secondary, the chloride comes and does SN2 on this carbon, because this is more hindered, and then you make the alcohol on the more hindered carbon, and the iodine ends up being on the less hindered carbon. That's if you have no tertiary carbon. But we found if there was a tertiary carbon, what would happen? A tertiary carbon undergoes SN1 very fast. So when protonation occurs, the alcohol leaves that tertiary carbon to put a positive charge on this carbon, we end up making the alcohol on the less substituted carbon, and the iodine ends up being on the tertiary. So tertiary carbons react fast in the SN1 reaction, and they end up getting the halogen. If there's no tertiary, then it's going to be an SN2. This is very similar to what happens with an epoxide. If you have a tertiary alcohol, a tertiary side to your epoxide, what happens is when protonation occurs, just like the ethers, the location of the halogen is dependent on the structure. And we classify it just the same way we did with the ethers, as looking at to see is the carbon primary, secondary, or tertiary. Well, let's first go with the tertiary. If you have a tertiary carbon in your epoxide, what happens when when the the epoxide is protonated? You get a large positive charge developing here, and then the halogen ends up attacking there. And notice we get inversion. You can't see it with this compound, but a inversion does occur on this carbon because the chloride comes in from underneath. And then this ring opens, and protonation, this protonated oxygen becomes alcohol. That's when we have a tertiary carbon present. If there's no tertiary carbon, you're not going to have that huge positive build up, and the reaction basically goes by SN2, and you see the halogen ends up on the less substituted carbon. Here's a picture of the tertiary type reaction. You see this carbon is tertiary, that one's secondary. If we use hydrobromic acid, protonation of this occurs. When protonation occurs, the ring opens a great deal and puts a lot of positive charge here. Now this oxygen hangs over that positive charge with its non-bonding pairs and ends up blocking the side of the ring where the hydroxyl group is. So the bromide attacks from underneath, and we get a trans halohydrin. We do not have the ring open to put positive charge on the secondary carbon because that's less stable. So we do not get this with the bromide on the secondary carbon. However, if this if you had a secondary and a primary carbon, things change, and the primary carbon then ends up getting the halogen. What happens when we have base? When we have a basic nucleophile, here we're showing hydroxide, it's always an SN2 reaction. So here the nucleophile comes in from the less hindered carbon and the ring opens. Now here we're just getting a diol, and there's no difference between the group that is made from the ring opening and the nucleophile that comes in. But we can have other nucleophiles. Here's an example of another nucleophile, a Grignard reagent. A Grignard reagent can come in. It's going to come in from the underside and then ring open and give you an alcohol. Notice this Grignard reagent is now attached to the carbon, and we have an alcohol. Other nucleophiles that will do this SN2 type reaction are amines, can do that. We can have all sorts of negative nucleophiles that would come in from the opposite side and always choose the less hindered carbon because an SN2 reaction is occurring. So, what is the summary? If you have acid conditions and a tertiary carbon is present, the nucleophile ends up on the more substituted carbon because we have this modified SN1 reaction. But if there's no tertiary carbon present, then you're going to have an SN2 reaction and the nucleophile is going to attack the less substituted carbon. If we have basic conditions, the nucleophile always attaches to the less hindered carbon because an SN2 mechanism predominates.